Part A, talking about a relative min. We know F has a relative min where F prime changes from negative to positive. So I'm going to look at this F prime row. I see negative, negative, negative to positive. Remember, that means your function goes from decreasing to increasing, making that a relative min at x equals 1. And it just says find the x coordinate. And then you have to justify your answer like we have on your blue packet. So I have on there simply F has a relative min at x equals 1 since F prime changes from negative to positive. That's what you need. Relative min at x equals 1 since F prime changes from negative to positive. Now, I actually thought letters C and D on this thing were pretty darn straightforward and pretty darn simple, even though you might have had some issues with letter D with the notation right there. We'll go over that. Letter B, it says, explain why there must be a value. That's theorem talk right there. So you got to know your few basic theorems that we talked about. If you need a refresher over these again, go watch that theorem video I made where I recap the theorems and I recap this blue packet there. The theorems are at the beginning of that video. Now, when you want to see a derivative is equal to 0, that's when I'm thinking Rolaids. If I'm supposed to show that like the y value is equal to something, that's an intermediate value theorem in between a couple of things. Or if I see a derivative is equal to a number, mean value theorem, a derivative is equal to 0, Rolaids theorem. So Rolaids theorem just says if you have a continuous and differentiable function, if you have the y values are the same, there's got to be a point where you turn around and go back in the other direction right there. And that point where you turn back and go around, that derivative is equal to 0. So you got to have a few things being true. It's got to be continuous, differentiable, and f of a has to equal f of b. The two y values are the same. So basically, we're pretending that the derivative is the original function. We're doing Rolaids theorem with that to show that the second derivative is equal to 0. So if I look at, it says twice differentiable function. That's good. That just means everything's smooth and continuous and curvy. Everything's good there, all right? So if we look at f prime, notice that if sum's differentiable, that means it's automatically continuous. So I just jotted down, f prime is continuous, f prime is differentiable, and then we're also supposed to show that the y values are the same. And then so if we look up here, we got f prime of -1 is equal to 0, and f prime of 1 is equal to 0. So I jotted down f prime of -1 equals f prime of a +1. They don't have to be 0, they just have to be equal to the same thing. But those are the three stipulations that make Rolaids theorem apply. It's got to be continuous, differentiable, and two y values are the same. If those three things apply, which they do, Rolaids theorem, you gotta write down Rolaids theorem. Rolaids theorem guarantees a spot where its derivative, the second derivative, is equal to 0. Because if those y values are the same, you gotta turn around, go back in other direction. That point, that's where the horizontal tangent line is there. That's where its derivative is equal to 0 right there. And in letter C and D, I thought I liked these problems a lot better. So letter C gives us this composition function, and we're just going to use our chain rule here. So if you have the ln of something, when you do the derivative, you're going to go 1 over that stuff, so that drops to the bottom, and you're going to times it by the derivative of that stuff. And then they ask us to plug in the 3's, and then you get these numbers from your actual chart. So f prime of 3, you're going to go f prime of the 3, that's going to be 1/2, and then it says f of 3, so f of 3 is equal to 7, so 1/2 over 7, boom, 1 over 14 right there. Now letter D, when it looks weird, like the BC's got to do like integration by parts sometimes, right? But if you're on this AB test, it's gonna be a normal integral, it's gonna be a UDU. And so if you let the U equal that inside function, let it equal that G of X, that inside function, and then, so if your U is equal to G, that means your DU is the derivative of that. So the derivative of G is G prime. And notice how you get those squiggles to match up, right? There's my G prime of X, there's my G prime of X. I don't even have anything to balance there. And then, so that stuff is handled. And then what your U is equal to the inside. So now you have F prime of U. And then when you integrate F prime of U, you get FU. That's just the only time I get to say FU to a student, and it's okay, you know, but you get this F of U right there because the derivative F of U is F prime of U. And then once you get that, plug your X's back in because these numbers are X's right here, not the U's. So plug in your G of X right there, then plug in, now you can use those X's, plug in the 3, plug in the -2, that's your fundamental theorem of calculus. So we'll get F of G of 3 minus F of G of -2. I think you know how to do those compositions from your algebra 2 and pre-cal days, but the G of 3 is equal to 1. That's where I got the 1. And then F of 1, that means F of the 1 is equal to 2. That I did that. So you could do this other one all by yourself there and get that -6 for your answer there. Pickles.